Good day, all calculus geeks out there. Hope you had a great Easter break. I also hope you don't feel offended that I chose not to send this video to you on Friday when I thought I could just get it out there and you could have it all the time and look at it and then Tuesday work on your assignments. But I decided not to send it to not tempt you to work during your break. You needed a break. I know I did. So uh, here we are. We taken our quiz, and the quiz grades were excellent. Uh, Even though I threw a few twists at you on how I presented it to you with the timing and switching the order of questions and answers, and you know, next time I'll probably try to put a couple different varieties out there. I'm playing with some tricks to keep you honest. But overall, I was impressed with a lot of the work. Uh, if you're truly doing everything that I'm having you do and you're performing at that level, you guys are learning something. What more can I ask? Now, if you're getting it through other means, then all you're learning is that you think you can beat the system, but not really. It has a way of fighting back. But we're on day 56, and we're talking about motion again. Problems with rectilinear motion. That just means moving in a bunch of lines, crossing lines. Uh, we're going to look at it graphical, numerical, analytical, and we're going to incorporate all that. And the main thing today is total distances, and along with that will be the word net and of objects over a period of time. Okay, so let's get on that. Trying to figure out how to get my cover page on my videos to be where I'm starting here, but it never seems to work. Bye, guys. Over and out. Keep these things in mind. What's he saying here? One, as you integrate a velocity graph, that's just a rate, any kind of rate. It doesn't have to be a velocity. It could be the amount of water being leaked out of a tank. It could be a rate per minute. The obviously the number of miles per hour, that's a rate. Maybe the number of buildings you are building per year, that's a rate. And he set it up from A to B. It just turns out to be the antiderivative of the integral. P being position most likely. V is probably what he's using for velocity. P is very common to be said position. So we know that if we take the derivative of position, we get velocity. So if we integrate velocity, we get position. He defines it now, where V of t represents the velocity and P of t represents the position. I guess it pays to read the whole thing first, right? And number two, if you're integrating velocity from A to B, your net distance will be the total distance traveled on the interval from A to B. If your velocity is always greater than zero, in other words, your velocity graph is always up here, then the total distance will also be the net distance. Number three, if you're integrating from A to B and you're doing the absolute value of your velocity graph, this would be definitely the total distance for sure. If you don't use the absolute value, like the example in step 2, it's because if you have velocity graph that is behaving more like this, then what happens is you have distance being accumulated that's positive if I was going from A, let me go to B here, B to B. You got your positive distance there. And what happens here, bounded by the x-axis, that's negative distance. Well, you could see how you could be traveling for some period of time and almost basically say you've gone 0 miles because you went one way, what, positive direction, your velocity was positive. Remember, this is your velocity graph. And then you stopped and went the other direction, and the two distances could cancel out, or at least part of it cancels each other out. So just because you traveled 9 miles one way and then went the other way 10 miles, it looks like you've only traveled 1 mile from your house. You know, you went 9 miles this way, and you, or I can even say, yeah, 9 miles, and then I traveled this way 10 miles. Well, I went 1 mile past your house. So it looks like I only went 1 mile. But you really traveled 9 plus 10. So that is why we use the absolute value here. If you want to guarantee total distance, what the absolute value does is when you take the absolute value of this region, it forces this picture to go up. That way we can now accumulate it with positive area. Now this part here always was positive. Okay. I suppose I could have drawn that picture over here and done the same thing, but I think you get the point that a particle could have positive distance, then negative distance. And total distance would be adding both region 1 and 2 up, even though it's negative. But you would take region 1 and you would add it to the absolute value of region 2. And that'll give you your total distance. That's your total. Now net distance would just be region 1 plus region 2. So even if one's positive and the other's negative, you could, the net distance could be smaller. The velocity of the particle is moving along the x-axis given by this function. Okay, it's just a parabola. And this is a non-calculator problem, so I won't have to pause and get a calculator or anything. If the position of the particle at t is 4 is 72, okay, he's telling me up front, at 4, I was at 72, whatever units. What's the position at 2? So this was a position at 4, and now I don't know what it is at 2. So I got a question mark there. So this could be a job for setting up my antiderivative of my velocity graph. And if you think about it, the only two positions I'm even talking about are 4 and 2. So 2 and 4 will be the ones I'll use. And I will not need to worry about a total distance or nothing like this, because we're just talking about how the position is moving. So when you do the derivative of velocity, you get the position. And we're going to plug in the top number first minus the bottom number. So there's my equation. Remember what we're looking for. We're looking for at 2. This is what we're looking for. So let's plug in everything I have. It's going to look like this. Integrate from 2 to 4 of 3t squared plus 6 dt will equal to, and I can calculate that in just a second by hand, p of 4 my position at 4 was given to me at 72, minus P of 2, which is what I'm looking for. So take a deep breath. Let's integrate this bad boy. That's 3t cubed over 3 plus 6t, all evaluated from 2 to 4, which will equal to 72 minus P of 2. So now I got to plug in, well, those two cancel, so I'll make it easier. Plug in the top number first, then I'm going to minus, plug in the bottom number. 4 cubed, 64, minus 2 cubed, plus 6 times 4 is 24. Now plug in the 2, that's minus 8 plus 12. And that altogether will be equal to 72 minus position at 2. 64 plus 24 is 88. Minus 8 plus 12 is 20. That would be 68, which is equal to 72 minus P of 2. So if I, let's see, if I take the P of 2 and move it to the other side, and move my 68 to the other side, I should get, and I know if I'm wrong, you'll tell me, P of 2 should be equal to 72 minus 68 is 4. Okay, let me study it and double check it. I'm confident with my answer. 4. Total distance of the same function. So that's your accumulating distance as you go. So he says I'm going from t is 0 to 7. When I integrate from 0 to 7 of v of t dt, I'd have to ask myself, do I need absolute value or not? Well, it's a parabola. As I recall, v of t is 3t squared plus 6. And if you want to just check it real quick, we're going from 0 to 7. What is this value at 0? It's 0 squared, 0 plus 6 is 6. And if I go to 7, 49 times 3, I don't know. It's almost 150. It's way up here. I do not need the absolute value because v of t is above the x-axis the whole time. So my accumulated area will be that whole area, region. Okay? So I'm okay. I don't have to use the absolute value. What if you did? Would it hurt? No, absolute value of positive is still positive. So it doesn't hurt. So I will integrate that again. And as you recall, it was 3t cubed over 3 plus 6t. I'll just write out t cubed plus 6t. This time I'm going from 0 to 7. And here goes. 7 cubed. Okay, that will need a calculator. Plus, that's 7 cubed plus 42 minus, plug in the 0, I get 0. So I just don't want to make a mistake in front of you. So I will go to my calculator and look for it. That's 343 plus 42. That's 5, that's 8, that's 385. That's my total. Could be feet, could be miles, could be inches, whatever the case is. Since there was no unit in the problem, you're not required to justify. Okay. I would really love you to say, total distance is. That way we know what we're doing. You have me write that on your paper stuff all the time. Second problem. The velocity of particles moving along the x-axis. That's very common to have a particle that is just moving back and forth. It starts here and it goes boop, goes backwards here, goes back here, stops here, just keeps changing directions. And this is a calculator problem, so I will have to pull out and get a couple screens out for you. And this is kind of cool because we get to integrate with our calculator, and we've had that lesson already. This is an exponential function times a cubic. Yeah, I have no idea what it looks like. It's not going to be human, that's for sure. If the position of the particle at t at 1.5 is 2.551, see how the weird numbers, once you have weird numbers and a weird function, it's calculator driven. What's the position at t is 3.5. So this is a position problem again. So I'm going to set my integral. The only two times I'm talking about are 1.5 and 3.5. Of v of t. Now, if I was doing the AP exam, I wouldn't even write it again. I would not waste my step doing this, because you don't have to. V of t is already identified right here. And I would just go right to my calculator and I would key that bad boy in, which is 0.5 e to the t. Here's another reason that this is calculator. You can't do this by hand. It's not. It is. There's other methods later on that you might be able to do this by parts, but probably not. So I'm going to go to my calculator and I'm going to key this in, and it's your function, wasn't it 9? And you got to put in the limits. Call this y1, because if you put that in your calculator as y1 equals this function, you don't have to worry. You're going to use it again. Why don't you just put it in your calculator right now and save time? All right, so I'm going to pause and you take a break, and you're going to do it too. Did you get it? 15.919, giving myself 3 decimals, is equal to P of 3.5 minus P of 1.5 equals to P of 3 is what I don't know. Or 3.5, I'm sorry. 3.5 is what I don't know. P of 1.5 I know was 2.551. So this one's actually easier, because all I got to do now is P of 3.5 must be equal to the 15.919 added to 2.551, which equals to 18.470, I think. Double check, 910, that's a 0. Yeah, I'm good with it. So this is the total, no, I'm sorry, this is the position we are in 3.5 seconds. We were originally at 2.5, now we're at 18.4. We've traveled a lot. B, what's this total distance the object traveled from 1 to 5? Well, 1 to 5 of my same function. Okay. It is going to be my p of 5 minus my p of 1. The problem is I have no information about p of 1 or p of 5. So I'm going to go right to my calculator. Fortunately, this is still in my calculator. I'm just going to go and do math 9 again, but I'm going to change my limits, and I'm going to record the answer. So go ahead, key it in, and see what you get. You really either should pause and do it and make sure you can get it yourself. Okay, I'm back. I hit graph first to see what it looked like from 1 to 5, and I saw that I am definitely going to need the absolute value. Did you notice that too? Hope you did. So we get 913.067. That's if you remember to absolute value it. If you did not absolute value it, you will get a smaller answer. Okay? Maybe I ought to put a picture of the graph just to show you what I was talking about. Graph is too big to show you the whole thing, so graph it yourself here. Okay, the graph of the velocity measured in feet per second of a particle moving along the x-axis is pictured to the right. Okay, there it is. So that's my velocity graph. Okay, it's always important to know which graph we're looking at. What is position at t if at time is 3? Well, I'm going to set this up exactly as I set up the other problems. I'm looking at it, and the only time periods that I'm worried about is 3. And I know that at 8, it was 1.2. No, I'm sorry, 12. So I'm going to set the integral up that the position, using the integral from 3 to 8 of v of t dt will be equal to your position at 8, my position at 3. So where am I going to get the answer now so I don't have a function? Go over here, 3 to 8. 3 starts here. 8 ends up here. I need this area. And I did them in different colors because one's negative, one's positive. So, and it looks like a lot more positive than negative. So let's try to calculate this area right here. It is a trapezoid. And this base is a distance of 3 to 6. That's 3. This distance goes from 3 to 4. So that's 1. So, but 1/2, 3 plus 1 times the cat just opened the door, so it's just going to bother me. This is the base of this particular trapezoid. So how long is that? Goes up to 5. So, whoop, wrong color. 5. So 3 plus 1 is 4. Half of 4 is 2. 2 times 5 is 10. And that's positive. Okay, let's calculate this area. That area is 1/2. The base of this triangle is 2. The height of this triangle is 2. Goes all the way to 2. So 1/2 times 2 is 1. So that's 2, and it's negative 2. You could say that the height was negative. So when I said that the height was 2, 1/2 the base times really a -2 gives you the -2 answer. So you put these together, you got a net of 8. Move back over here, and I'll put my 8 here. My position at 8 was 12. My position at 3 is what I'm looking for. So 8 minus 12 equals -p of 3. That 8 minus 12 is a -4 equals -p of 3. P of 3 must be 4. My original my position at time t is 3 is 4. 4 feet. Okay. What is the acceleration when t is 5? Well, what's acceleration compared to my velocity? It's the derivative of velocity. So acceleration at 5 will be my slope of that graph at 5. Since this is a picture of v, 5 is about here. I just need the slope of that line. That's what v prime at 5 will be. So v prime at 5 will be the slope. So this y value is a 5. This y value is 0. This x value is 4. This x value is 6. 5 over a -2, -5/2. I do expect it to be negative. -5/2. Acceleration will now be feet per second squared. Where's my round of applause? What is the net distance of this particle as it travels from 0 to 10? Since I only want net, I don't really care about positive, negative. Net means how far are you from the house, no matter how many times you turned around and went back and forth. I don't care if you ran all day long. If you end up passing out 1 block from your house, well, then your net distance is 1 block. No one's going to believe you that you went more than that. So I'm going to integrate from 0 to 10 of v of t dt. So 0 to 10. Oh, that's the whole picture. That's going to be all of this positive area minus all of this negative area. So I just got to figure out, let's see, this is a trapezoid from 0 to 6. So I got to separate that. Base 1 is 6. Base 2 is 2, 2, 4. So that's a 2. So 6 and a 2. So it's 1/2 times 6 plus 2. The height is 5. Then this area is going to be a negative area, so I may as well take it 1/2. The base from 6 to 10 is 4 times the height. This is where your negative comes in. -2. But I already took the negative out here, so 2. 6 plus 2 is 8. Half of 8 is 4. 4 times 5 is 20. 4 times 2 is 8. Half of 8 is 4. 20 minus 4, 16. And our unit is feet. That's my net. What's the total distance? Oh, I knew he was going to make me do that. Total distance is the same problem. 0 to 10, but it's the absolute value of v of t dt. So just make sure that, look at what I said before. It's the same two pieces. it's still going to be the 20. And feel free, absolute value of 20, right? Plus its area. What area? The absolute value of that negative 4 is 4. So it should be just 24 feet. Chew on that for a minute. Okay. Now we got table. We've done this before. I think these review our Riemann sums, which is good. The table above shows the values of velocity in meters per second. The particle is moving along the x-axis, and here are selected times. Look at the times though. 0 to 3, that's added 3, plus 3, plus 3, plus 3, plus 3, plus 3. At least those are equal intervals, and why it makes it easy, because he first of all wants to know what does the integral from 0 to 18 of v of t represent. Well, that's the whole thing. So I'm going to write it in a complete sentence. The integral from 0 to 18 of v of t dt represents, now it represents the net distance traveled from t is 0 to t is 18. And net distance equals total distance if v of t is greater than 0 on the interval from 0 to 18. And in this case, positive, 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 positive. So I would be okay to call it, if you would have said that at the beginning, total distance, we are correct. But you never know. Now we're going to use left Riemann sums, 6 subintervals. These are left of equal length. I think what he means by intervals is equal length. That means the width of each rectangle, this piece here, and estimate the value from 0 to 18. So he wants 6 of them. So this would be a rectangle. Then I need to share the endpoint. There's one. Then I'm going to share this one. Share this one. Share this one. So I got 1, 2, 3, 4, 5. I need one more. 6. There they all are. And the beauty is, from 0 to 3 is 3. From 3 to 6 is 3. From 6 to 9, they're all 3. So my area, my distance, I should say, my total distance equals the integral from 0 to 18 of v of t dt is approximately my length times width plus length times width plus length times width plus length times width. 1, 2, 3, 4, 5, 6. And if you really want to be technical, it was 1, 1, and then 1 or 2, 2, 3, 3, and so forth. But we know that the widths are all the same. So I'm going to factor out the widths. So that leaves you 3. With this length, the height of the rectangles, the lengths come from, he wants left, so it's going to be this one and of this rectangle, this one of this rectangle, this one of the. So it's basically going to be 1, 2, 3, 4, 5, 6, not 7, because this will be the left of this last rectangle. So it's going to be 2.3 and 2.7 plus 2.0 plus 1.3 plus 1.0. Okay, so do I dare do it in my head? Every time I do it in my head, I always make a mistake. 2, 4, 6, 7, 8, 9. I think it's 9.3 times 3. That would be a 9. 27.9 units per meters. Let me know if I'm right. 2.3, 2.3, 2.7, 4, 5, 6, 7, 8. Oh, no. Let's see. 2.3 is 4. That's 5, 6, 7. That's 8. That's 9. It's 3 times 11, 33 meters. 33 meters. 2, 4, 5, 6, 7, 8, 9, 10, 11. Yes, okay, got it now. Now use the right. Okay, so now the only difference is it's still a distance of 3, but now we're using the right side of each rectangle. So I'll be using that height, then that height, that height, that height, that height, and that height to be the right side of the last rectangle. So I'm not using the 2.3. So everything stays pretty much the same. My total distance is approximately the integral from 0 to 18 of v of t dt, which equals the 3 pulled out. Now it's a 2.7 plus a 2 plus a 1.3 plus the 1 plus the 1.7, this time plus the 2.1. So go ahead, add it up. 3 times 10.8, which is 24 decimal 2 3 332.4 meters. Use the midpoints. All right, midpoints. Midpoints are going to use. Oh wait, he didn't say the same 6. He said only 3. So if I'm only using 3, then this would be a rectangle. That's 1. This would be a rectangle. That's 2. Then this would be a rectangle, giving me each the midpoint in the middle of each of those. Now, the width from 0 to 6 is going to be 6. From 6 to 12 is 6. And from 12 to 18 is 6. So my total distance now will be approximately the integral from 0 to 18 of v of t dt will be 6. And I'm going to use 3 midpoint heights. 2.7, 1.3, and 1.7. 2.7, 1.3, 1.7. Did I say it right? 2.7, 1.3, and 1.7. That's 6 times, it should be easier to do 3 numbers. 2, 3, 4, 5, 5.7. If the cards are right, that's 40. 42, the decimal, carry the 4. 34. 34.2 meters. Use the trapezoidal sum of 6 subintervals. So I'm back to all 6 again, using trapezoids. I don't know about you, but I'd either have to draw a whole new box or I'm just going to 6 of them again. So I'm back to my original. These two go together. 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 So I got 1, 2, 3, 4, 5, 6, which will be the parts of my trapezoids. So my trapezoids are still going to be this distance, and that's 3. Now this has a height of 2.3. This has a height of 2.7. So as you can see, there's a trapezoid there. Now this trapezoid, the second one, the first side has a 2.7. Well, that's this leg, and the other one, and it's still a distance of 3. And then this one has a distance of 2. So it's not as tall. So it's going to go like that. And now the third trapezoid goes up to 2, and the other one is 1.3. So as I can see, as that goes out to 3, 2, 1.3. So you see what's happening there? I'm not going to do them all that way, but that's what's going on here. So my total distance will be the integral from 0 to 18 v of t dt, which is all of these were approximates, by the way. I hope you understand they're all different because we're approximating with different things. The height of each trapezoid is these distances here because these two sides are parallel. So these are legs. The legs are always parallel. That's the height of the trapezoid. So each of those are 3. So it's 1/2 times the height, which would give me 3/2. And the trick was you have 1 of this one. So that's 2.3. Then I have 2 of the next one, which is 2.7. Then I have 2 of the next one, which is 2. Whoop. Then 2, what's after the 2, was a 1.3. Then I have 2 of the next one, which is a 1. 2 of the next one, which is a 1.7. And then the last one, you only have 1 of those, 2.1. So I'm going to go and plug it in my calculator and see if I get it right. I'll be right back. I got 32.7 meters. Find the average acceleration. Okay, average acceleration. We've done this before. Please don't just start doing a slope. Put acceleration, average, or average acceleration. Do something. Would be the slope of the velocity curve. So it would be, if I'm going from 1 to 9, would be v of 9 minus v of 1 over 9 minus 1. V of 9 should be up there in the graph. V of 9, 1.3. And what did I say? 1.3. And what did I say V of 1? It's 3. Three. Minus V of 3. Is that in the graph? V of 3, 2.7. 1.3 minus 2.7 over 8, which is a negative 1.4 over 8. 1.4 over 8 is negative. I'm going to use my calculator. It's not an 8 on there. I know. I see it before you yell at me, guys. It was a 9. I fixed that 3. So that should be a 3 also. So it should be over 6. And so that should be a 6. All right. Negative. Let me do it again. Be right back. Negative 0.2333. It's average acceleration, meters per second squared. And what value of t in the table is this average acceleration approximately equal to, and explain why? Well, let's first go look up. What value gives me the same answer? 0.2333. Between 3 and 9. Between 3 and 9. I'm in this block here. It was in the middle there. We did the slope of a secant. That's called the mean value theorem. So we would say that, explain the reasoning by the mean value theorem, V of 6 would be equal to, not V prime of 6, would be approximately or equal to the average acceleration. The average acceleration. To begin, guys, I want to stress to you, I give you credit just for doing these problems. And I know some of you do not have your integrity, and you don't even know what the code of conduct is about being honest. But if I wanted to hide where this came from, I would make it harder for you to find it. I am telling you where it is. This problem looks so similar to one we just did, and it should make you excited that you have a chance to work on a problem for the AP test, since this year's AP test is only 2 problems. You need to work these out with integrity. Try to do these. I mean, if you turn this into me with exactly the answer that comes from the College Board, you don't think I know that? Now, is there value of still just looking at that and doing it? Sure, but you didn't learn. You might have learned something. Do them. Annotate it. Learn from it. So I'm going to go back. And then there's your homework.